Hello everyone, my name is Elliot McDonald and I'm a recent graduate from Whitnall High School, as well as an avid programmer. In the first months of the COVID-19 pandemic, I learned how to code in Java so that I could create different projects that could run quickly on a variety of programs. For the last 4 months I've been engaged in a coding passion project of mine that is now over 1,000 lines of code, and today I'd like to share and explain that project with you all. I call this project SMBAI, short for the Super Mario Bros. Artificial Intelligence. The idea of this project was to create from scratch a weak AI capable of playing to complete the first level of Mario in the shortest amount of time possible, while getting better and better at it over time. Quick disclaimer before I go any further, while I was the sole programmer and creator of the artificial intelligence program I created to work with the Mario game, the Java version of Mario was not created by me and I don't take credit for it. It was an open source project on GitHub that I used as the foundation for my creation. As I was saying, however, the AI that I created intends to beat this Java version of Mario that I found. There are two general ways of completing such a task: teaching AI to make a series of actions and rewarding it when the actions are correct, or instead teaching it to contain a series of strategies and reactions to stimuli and rewarding it when those strategies work. And so that means that in that method, you are telling the Mario how to react to different enemies, different walls, different ceilings, all of those things in its environment. Since I wanted to make this AI able to play multiple levels of Marios, not just the one, using the second method works much better. Therefore, the idea behind this artificial intelligence I created is that it creates a randomly generated set of strategies to use that are triggered based on being a random distance away from a random type of entity, chosen from the list of Goombas, Koopas, walls on the right, walls on the left, ceilings, and floors. Using these entity types, the AI is able to react by running, jumping, moving left, or moving right. It produces random strategies using these actions and trigger types, as well as using a random trigger radii for how far away the trigger type must be for it to trigger, and random durations for which those actions are then performed. All of these random actions lead to AI agents, which are seemingly terrible at the game in the first trials. However, the learning aspect of the AI is what really comes into play. While I was never given a formal education on how the concepts of AI function, I decided to utilize concepts about learning that are easy to understand from a logical perspective, and what I chose for that is evolution. The entirety of the learning process which these agents undergo is based on the principles of evolution that I've learned from my biology classes. This means that agents in the first generation that perform best are then utilized in the creation of the next generation of AI. Each new generation is created by the regeneration protocol, and it's categorized into 3 separate types known as purebreds, hybrids, and beasts. These agents, known as purebreds, are direct descendants of the top successful agents of the previous generation, without any type of modification. The agents known as hybrids are a type of agent that is produced as a product of the traits of the purebreds, as well as some minor mutations. The way in which this is performed is by having each hybrid copy a random number of traits from any random purebred from the generation before. This allows them to have a combination of the most successful traits of the previous generation. In addition, they're also given minor mutations of sorts, and this mutation method goes through each quantitative value of the hybrid agent's strategies and changes them slightly either positively or negatively. That includes the action durations, the trigger distances, and other types. The last type of agent is known as a beast. Such as how it sounds, I gave them this name because they are completely wild compared to their learned sibling agents. These beasts are produced by the gene flow protocol, in the same way as agents are produced at the beginning of the game. This allows for new strategies to enter the gene pool and provide strategies that were not originally in the gene pool a path to success. So we've talked about the regeneration protocol and its algorithms, but what about the methods and classes used to allow the agents to both receive input about their world and output those actions into the world? These two objectives can be broken down into 2 primary classes, called the obstacle analysis class and the button execution class. The obstacle analysis class fits its name, as its intention is essentially to view the most important aspects of the world and pass them on to the agents performing their run. The obstacle analysis class passes in the position of the nearest enemy, the nearest wall on the right, the nearest floor, and the nearest ceiling into the agent, and allows the agent to decide what they want to do with that information. The button execution class takes the desired motion of the AI agents and converts it into what I call virtual keyboard input. This virtual keyboard input makes the game think that you are typing something on the keyboard to perform whatever action the agent wants to take, but in reality it is just the program itself taking those actions. general nature of this project made it so that when I was programming, there were very few aspects of the code that I could actually fix bugs in what I was writing. What I mean by this is that because every generation is virtually random, only the superficial parts of the UI were actually obvious when they were having bugs. If there was any bugs in the AI algorithms itself, it was nearly impossible to discover and pinpoint the problem for. Most of my bugs in the AI contained repeated hours of painstaking double-checking through each pathway the AI would go through to see if I could spot bugs, without ever seeing them happen in the game itself, because of the fact that everything is random and so there's no way for me to know what's bugging and what's not. Therefore, this whole project was somewhat of a leap of faith, because if it turned out that the AI didn't learn to the level it was supposed to, there is very few ways I could really figure out what was causing the problem, due to the complexity of these algorithms. However, that made it all the more rewarding when I soon observed the AI learning not only in ways that I had expected it to, but also in ways that I had never thought possible. Some agents performed as I had hoped by jumping at certain trigger points to get as far as possible, but then other agents took the level and strategies to survive in a whole different way that I had never thought of. I'm talking about the agents that I now call hunter types. The hunter type agents are names I gave to the agents that have somehow identified a way to track enemies in their vicinity all the way into the ground so they eliminate each and every enemy in the level. They do that by jumping over the enemy and then following the enemy left and right all the way down to when they get back down to the ground so they land on top of each and every enemy in the level. And what makes these hunter types particularly interesting is that they shouldn't be physically possible to exist. Based on the information that I talked about earlier with the optical analysis class, I tell each agent during their run how close the enemy is to their position, and they decide what they want to do with that information. However, I never tell them whether the enemy is on their left or on their right. Based on that information, when the AI is in the air, the hunter types should have no reason to know whether the AI is on the left or on the right of them, so it is difficult to understand how they are able to track the enemy all the way down to the ground and land on them every single time. However, they are able to do it anyway. Another way to state this is that the AI has learned past what I've given it the tools to do, and I find that impressive. The last part of this project was the creation of the user interface and the accessibility functionality. This began with the creation of the saving and reading class files, which allows for the serialization of agents into custom extension files called .SMBAI. This saving system allows you to pause the development of the agents at any point in time and resume it at a later date. Since each of the agents are sorted, the best agents are always first in the list, and so an option that is given in the launcher is to ask if you'd like to restart from the beginning of each generation. If you do this option, you'll be able to see the most successful agents first. As for the success of this algorithm, in a generation size of 100 with a selectivity factor of 20% and a gene flow factor of 10%, we usually see a few agents able to complete the level by around generation 3 or 4. Some agents develop other powerful strategies that allow them to make it through the selection process, but may not actually finish the level. Regardless, you can see how effective these algorithms end up being in allowing the Mario AI to finish the levels themselves.